So what he's primarily concerned with is the instruction/value part of this chart. He wants us to fill in the blanks like I did here. And with the symbolic representation section of this IAS instruction chart. Now, I'm not showing all of it, but in this particular operation, you wouldn't need to know what's on the second page because we're not performing any arithmetic operations involving multiplying or dividing or any shifting instruction. So you can see you have three columns. One has the location, as in the location and memory. One is for the instruction/value, and the other is the comments, which is telling you what is being done at that particular step. And as you could look at the location part of this column, the location column, you'd see 0, 1, 2, and 3. And it's defined that way because this is where you're defining and initializing your variables that you are to use. Like how in Java you'd have like int I equals 5 or double x equals 12 or something like that. And so then it starts doing 4L, 5R, 5L, 5R, etc. And the reason why it's formatted like that is because this is the way memory was stored in IAS instructions. You can see this in Chapter 1 notes where there's a left instruction and a right instruction in an instruction word, each part containing an 8-bit opcode and a 12-bit address. Now, this is a simplified form of it where the address is just like 1 or 2 characters. And we're not really concerned with the opcode here. It has nothing to do with actually performing this operation. So you'd be reading the instructions right here, and you would look at the symbolic representation and write whatever is happening in the comments into this box right here for the instruction/value. So the first step is loading the letter N into the accumulator. That's what AC is standing for. And we're defining that as some constant N in memory location 0. So there are two instructions we would be using for data transfer in this operation. One is the load, and the other is the store. The load involves transferring something from a memory location into the accumulator. The store involves transferring the contents of an accumulator into a memory location. In this case, we're putting N into the accumulator, so we would be using the load operation. And X is the parameter, as in what memory address we're referencing here. Since N is being stored in memory location 0, we're putting 0 into where X would be. The next step is a subtraction operation. We're subtracting I, which is being stored in memory location 2, from N, which we have loaded into the accumulator in the previous step, and we're loading that back into the accumulator. So that you look at the arithmetic instructions, and you'd see sub m of x. You'd be subtracting m of x from the accumulator and putting that new result in the accumulator. So since I is being stored in memory location number 2, you would do the sub m of 2 operation. Now these next two steps he has already done for us. These are conditional branching, in which we're testing a specific condition if the accumulator is greater than 0 in this instance, and we're jumping to a different part of the code depending on this condition. This is like the equivalent of like if-else statements in Java or any other programming language, where the argument is the location, at least the numeric part of the location, and then you'd be jumping either to the left half, well, it's down here, down to either the left half or the right half of m of x in this instance. Left half involves 019 in the second part of this argument. The right half involves 2039. So in this first step, if the accumulator is greater than 0, we would be jumping to memory location 6, and then 19 refers to L. So we'd be jumping to this instruction right here. Else, if it is equal to N, the operation is done. So we would be jumping to 5R, because 5 is right here, and 2039 refers to the rightmost instruction. Well, this is 5R, so it's jumping to itself, meaning the operation is done. But we're not done yet, so it would hit 5L the first iteration around, and then jump down to 6L right here. Since this instruction involves getting loop counter I, so we would have to load variable I into memory, so it's load M2. Next step involves adding 2I and storing that in the accumulator. Now this is basically an incrementation operation, but these old IAS computers didn't have some sort of mechanism to increment. They didn't have, like, you can put a variable and tack on 2 plus signs at the end, like how you can do in other programming languages like Java. So we're storing a 1 in memory location number 1, where it says constant loop counter increment. Well, that's the value we're using to increment. So we're adding the contents of memory address 1 to I, and we're storing that into the accumulator using the add operation in this chart right here. Then we're using the store operation. The store is different from the load operation, in which we're transferring contents from an accumulator into a new variable. Since we're putting it in I, we're storing the contents of the accumulator in memory address 2 right here. So that's why it says store M2. Now, since I was what you did in the last step, it's now what the accumulator contains. The next step involves adding y to that. Y is the variable. It's the sum of all the x values. It's stored in memory location 3. And so you'd be performing the add operation, and the argument would be 3 then. Then you're putting the contents of the accumulator back in the y. So you'd be using the store operation, but instead of 2, you'd be using 3 now. And then this last step involves unconditional branching. Since there's no condition being tested, it's a loop, so it's just looping back to the top. You can notice how there isn't a plus in between the symbolic representation part because it's unconditional. So you're jumping to the memory address location 4 as part of the instruction in the leftmost, so it's 19 rather than 2039, so it's jumping back up here. So that's how you basically do it. It shouldn't be that hard to do in the test. You basically just read the comments and you fill in this part, where the symbolic representation part, into these blank spaces.